Good day. I am Peter Rony, Professor Emeritus of Chemical Engineering at Virginia Tech in Blacksburg, Virginia. This YouTube video is about enrichment chemistry, and before I go further, I need to define enrichment. And here is a definition that I found on Google. It's a noun that means the act of making fuller or more meaningful or rewarding. So this definition is precisely the point of my use of the word. I have just studied the Amazon.com listings of General Chemistry textbooks. And here are examples of the front covers of the ones that I looked into. So, what are my conclusions about these textbooks? They all seem to lack what I call qualitative system identification. And what is that? I will discuss it later. These books are expensive, averaging $200 at Amazon.com for a hardcover new book. The renting of a textbook is new to me, and these textbooks are well illustrated and organized. At Amazon.com, I really appreciate the Look Inside feature, which allows me to view the table of contents and also the first chapter. Unfortunately, no student discounts are available. Well, I thought that this YouTube video would be initially directed toward teachers and students, but as I worked on it, I realized that really the focus of this video should be on textbook authors. And so I asked a couple of questions. I've been an author of a variety of textbooks on digital electronics and also microprocessor interfacing starting in 1974. So I ask, are you on a lucrative treadmill? There are a lot of general chemistry students that take such a course every year, so the national sales totals of such a book or such books should probably number at least in the hundreds of thousands. Are you subject to what I call the tyranny of revision every 2 or 3 years? And if you need to revise your general chemistry textbook, have you considered the possibility of adding engineering material to your revised textbooks? If your answers are generally yes, I suggest that you consider the content of my Enrichment Chemistry series, especially the complete book at a website called Teachers Pay Teachers. While thinking about textbooks, I have also thought about the plight of adults who have completely forgotten their general chemistry course. There should be tens of millions of such adults in the United States. And I believe a worthy objective for general chemistry textbook authors should be to increase science literacy for millions of adults. A light textbook would be available on Amazon.com, and it would be marketed by methods other than university reps and chemistry conferences. Most important, the light textbook should be substantially less expensive than a student textbook. It should be more qualitative and certainly focus on real-world systems. it can be less quantitative, and therefore no need for student manuals is the situation. And since they are not driven by chemistry course sales, there's no requirement to revise the LITE textbook every 2 or 3 years. And you need not worry about STEM guidelines, which applies to students and not necessarily to the general public. And I suggest that you incorporate in the LITE textbook what I call qualitative system identification. And you need not have hardcover books. You can rely on softcover and ebook versions. Well, why am I doing this? Well, I'm a chemical engineer, and I would like to impact general chemistry education worldwide. And why? Because I view the teaching of general chemistry differently than the view of a chemist. And I believe that my view is appropriate and valid today. My background, I am a chemical engineer by profession, and I've had 6 years of industrial experience and 31 years of academic experience. Since I'm Professor Emeritus, I don't need to pursue federal grants. The proposed mission is to really impact, as I said, general chemistry education. This is not restricted to the United States, but is an opportunity that exists worldwide. Now, I'm 76 years old. I'm probably too old to become a social networker. I am tweetless, textless, Facebookless, hashtagless, but I certainly use email frequently. I use a dumb phone instead of a smartphone, and my grandchildren consider me to be hopeless. I like this image. It has a bright yellow color, and it informs me and suggests to you that I am enjoying my 12 years of retirement. And one of the pleasures of my retirement is that I do not have to worry about a dean of engineering or department head of chemical engineering feeling that they have a better idea of what I should be doing with my professional career. For example, neither has thought highly of my book writing activity. And right now, I'm certain that they would prefer, if I were still teaching, that I spend my time pursuing hundreds of thousands of dollars of research grants. When in fact, my wife and I would be delighted for modest royalties so that we can visit our children and grandchildren more frequently. This is not my first effort to make available my ideas about enrichment chemistry. First, there is what I call the Enrichment Chemistry series at Amazon.com. I started with a complete ebook, which I will describe in a moment, but I've carved out 12 shorter ebooks. The 12 ebooks total 640 ebook pages. There is a total of more than 500 color images, and they all use the Kindle Mobi file format. If you want to find any of these ebooks, go to Amazon.com and search for the phrase Enrichment Chemistry Series. And when you go to the page, or 2 pages, you will see, I think, all of my 12 ebooks. Now, I plan to revise only books 2, 4, and 5 later this year. Here's where I started. The ebook is called Enrichment Chemistry Complete. It has a total of 640 ebook pages and more than 500 color images. And in comparison to Amazon.com, this single large ebook contains all of the ebooks in a single PDF file. How do you get this ebook? Well, you go to teacherspayteachers.com, you search for Peter Rony, and then on the resulting page you will find Enrichment Chemistry Complete, and you can download your initial copy for $10. What's really nice at TPT is that additional licenses for students can be obtained at a 50% discount. I don't expect that Enrichment Chemistry Complete is a substitute for introductory chemistry or general chemistry. It is not. It is an enrichment of the chemistry experience. Because it is so inexpensive, I ask you teachers whether it could be an effective supplement to a course textbook. Now, this year, 2015, I am creating a series of videos entitled the Enrichment Chemistry series on YouTube. This is July 2015, and I just started to create such videos. They are free, and each video will have a PowerPoint style that includes audio narration, and the uploads to YouTube are Windows Media Video File downloads, namely WMV, of the PowerPoint videos. And once you go to YouTube, search YouTube for the keyword phrase Peter Rony. As I've been looking at General Chemistry textbooks on Amazon.com, I came across this image which I really like. It's from the textbook, the title which is given, Fundamentals of General Organic and Biological Chemistry, 7th edition. And here the image states that chemistry is the central science. And in this case, the authors have focused only on health-related disciplines. Well, I see enrichment chemistry in a somewhat similar light. Not that I have written deliberately, but my complete ebook contains material that is associated with a variety of disciplines. Now, the most important material is related to chemical engineering, and especially human nutrition, some biology, and certainly environmental sciences. But the first book or two deals with astrophysics and astronomy. And why? Because I have been interested in how atoms in the periodic chart were created and why they have the different abundances that they do. So I feel that chemistry is a central science. In fact, I call it the queen of science. Well, let me get back to enrichment chemistry. I believe that it is a different and easier way to learn important principles of chemistry and chemical engineering. And here is really the most important message of my enrichment chemistry approach. You need not concern yourself with electron orbitals or hybrid orbitals. In fact, if you remember the public, do you even remember these two concepts? Well, my message is that molecules are the smallest units of meaning in chemistry. I got this quote from Philip Ball in one of his public-oriented books. Well, that's a pretty good statement. It's very appropriate because there are tens of millions of different molecules, and they come in a variety of categories, only a few of which are listed here. There are the small molecules: oxygen, nitrogen, carbon dioxide, hydrogen, methane, carbon monoxide, sulfur dioxide, and so forth. You already know and have heard of these small molecules, know what they are. However, a category that is very important are vitamins such as A, C, D, E, K, and the B group of vitamins. These are important in biochemistry and especially in human nutrition. You are well aware of biological polymers such as DNA and RNA, and on nutrition labels you are also aware of fatty acids and carbohydrates. For years you have been warned about hazardous molecules: DDT, PCB, poisons, explosives, and synthetic polymers such as polyethylene, nylon, polypropylene. I mentioned the phrase qualitative system identification. So what is this phrase? Well, it pertains to the question, what do you need to know about a selected molecule? And here are the questions. What is the molecule? Where is the molecule located? What amount of the molecule is present in each of its location? And what is the molecule doing in each of its location? So this is sort of qualitative, except for amount. The first, second, and fourth questions are qualitative, which makes them easy to answer. Well, here we have 4 qualitative questions. Is there any general principle that can be applied to each of these tens of millions of molecules? My answer is yes. The general principle involves the concepts of identity, location, amount, and rate processes. And these are the concepts that are the basis of my approach, which is called enrichment chemistry. So the first question I ask about a complex system are the 4 shown here. What is the molecular identity of a molecule that is of interest? What is the molecular location, actually locations, of this molecule? What is the molecular amount in each of these locations? In many cases, this amount is difficult to measure or estimate, but it should be acknowledged that you need to know how much of a molecule is located in different places. Finally, there is molecular rate process. And for general chemistry textbooks, they focus on reactions, but they do not focus on the processes of diffusion and convection. Well, of these 4 concepts, I'd like to focus the rest of this YouTube presentation on location. The message I want to give you is a molecule can be in several different locations simultaneously. Well, you already know this because you know that a molecule could be dissolved in a liquid phase, such as water, and simultaneously be present in the gas phase, such as air. But a molecule can also be dissolved in a polymeric solid, organic polymer. It can also be present at the interface between the gas and liquid phases. It could be adsorbed on a surface. Note the letter D, adsorbed. And it could be bound to a biological molecule in a biological cell. So let me give you some examples of location. Here we have a household water purifier. I guess water ends at the tap water ends at the top and comes out the bottom as purified water. Now, the key component of this purifier is what is called activated carbon. There's a whole bunch of activated carbon. And activated carbon is a remarkable solid. It has a very large internal surface area, and it's designed to attract and adsorb with a D, organic pollutants like phenol, chlorinated hydrocarbons, and get them out of your tap water. So activated carbon is a location, and the specific location is your molecule of interest that is on the internal surface of the carbon. Well, at the upper right is a different type of system familiar to you. It's oil and vinegar salad dressing. And here we have a little decanter where we pour in a bottom layer, which is vinegar, and a lot more of a top layer, which usually is or should be olive oil. And then these black particles are herbs and spices. And I think in the bottom layer you may see some little pieces of onion. So to prepare Italian dressing, which is what this is called, you put all these ingredients in and close the top and shake vigorously, probably for 10 or 15 seconds. Once you finish shaking, you put the decanter on a surface and you let it sit for several hours, after which you can shake the mixture again. And the idea is to get the organics in the herbs and spices solids to be infused into both the oil and the vinegar aqueous solution. So if you have a molecule, let me call it acetic acid, it would be found in several locations. First, most of it in the aqueous phase, this low pink-colored liquid, and then some of it in the olive oil phase, and some in the air above the olive oil. So you open the decanter and smell it, you'll have a vinegar smell. So you have several locations in this simple system. Let me now move to the lower left image. This image depicts a surfactant, which I believe is a very interesting type of molecule. It's a long molecule. On one side it has an inorganic end. The inorganic end could be a carboxylate, a sulfate, or something, but something ionic that is attracted to water. Then for the rest of the molecule, it's a hydrocarbon. It has a very long hydrocarbon chain, and such chains are not soluble in water at all. And as you can see, the surfactant molecules align themselves in the following way. The heads, the ionic heads, are dissolved in the water phase, and the nonpolar organic rest of the molecule is oriented above the water phase. Now, the phase above the water can be air, or it could be organic liquids such as olive oil. And what you have done is have a surfactant film on top of the water. And why would you do that? Well, such a film represses the evaporation of water into the air. So the film just serves as a barrier, and water molecules have a problem penetrating this very, very thin surfactant barrier. Now, surfactant molecules are also useful to create foams and emulsions between water and oil, and they are used in cosmetics. Now, in the lower right, we have a biological system. We have a simple example of a receptor. Now, if we consider or select a drug molecule, which is this little red thing, as our molecule of interest, then this location where the drug molecule is attached to the receptor is considered a location. And there are hundreds of thousands of these type of receptor locations in a single biological cell. Well, a lot of what I've said may seem rather esoteric and theoretical, so let me now illustrate at least one important principle of enrichment chemistry by a practical example. We start with a molecule, a dangerous molecule called DDT, which is short for dichloryl diphenyl trichloroethane. Here are two chloride atoms, and here are the two phenols. So this is chlorophenyl, you have two of them, so I have dichlorodiphenyl. And then here, the red entity is an ethane structure, and you have three chloride atoms, and so the structure is called trichloroethane. And I got this image from this website. And if you see this URL at the bottom of subsequent figures, what it means is that I'm giving credit to the location where I obtained an image. I really like Google images, and I use it all the time to search for keywords. And this example, the keywords that I've been using are bioaccumulation and biomagnification, and also amplification. And if you were taking an environmental science course or group of courses, you would encounter these keywords regularly. Before I go further, here is an excellent PowerPoint presentation that I encountered on the internet. I don't have the URL, but if you use Google search for biological magnification, you should locate it. It's a PDF presentation, and I'm very impressed with it. Well, I now would like to focus on the role of DDT in an ecosystem. This is an environmental science topic. Well, I take you to Borneo, an island in Indonesia in Southeast Asia, and I don't know how many decades ago, but here was the issue. There are lots of mosquitoes. And why? Because there's a lot of rain in Borneo, and the atmosphere is humid, and there's rapid vegetation growth, and lots of mosquitoes, which cause malaria. So the friendly folks in Borneo said, well, let's get rid of the mosquitoes and let's spray DDT all over. Unfortunately, there was an unintended consequence. In fact, there were two of them. So let me look at the top one. DDT is an indiscriminate insecticide, which means that it will not only kill mosquitoes, it will kill many other types of insects. In Borneo, the case of it killed parasitic wasps, which were plentiful and kept control over insects. So this is a natural predator for what? A caterpillar. And this caterpillar is called a thatch-eating caterpillars. So because the parasitic wasps were killed everywhere, the caterpillars just kept multiplying, and there was an abundance of caterpillars. And what happened? Well, they ate the roofs off the villagers' houses. This is sort of a funny example, but it's quite tragic. So this is the top path, and there is a bottom path, which I will not discuss. And you can learn more about this ecosystem situation by going to this URL at the bottom. Now, a more common example of DDT in ecosystem is the following. And this goes from dissolved DDT to zooplankton to small fish, large fish, fish-eating birds. And I'll show you another image, but this is an example of bioaccumulation. DDT in water is very insoluble. However, zooplankton, such as in the ocean close to shores, concentrates enormously the DDT. So if you have a pound of zooplankton and you measure how much DDT is present, you'll learn that the amount of DDT to the amount of zooplankton is in the neighborhood of 0.04 parts per million. Well, small fish eat the zooplankton, and the DDT that is contained in the zooplankton is transported within the fish to fatty portions of their cells. Well, large fish eat the small fish, and large fish probably have more fatty regions than small fish. And then what happens to the large fish? Well, they're caught by eagles, cormorants, other birds, and when you analyze the concentration of DDT in the birds, it's really very high, and the fatty regions is 25 parts per million. So if you go from dissolved DDT to the DDT in the fatty tissues of birds, the amplification is 10 million, which is huge. Okay, let me continue. Here is another image that makes the same point, and we start with dissolved DDT but then another location is sediment, so the DDT adsorbs on the sediment at the bottom of, say, a lake. And then there's vegetation, and there are different types of fish. There's also algae, and finally at the top of this chain there's a cormorant. The cormorant eats the fish eats the algae and zooplankton. The zooplankton they don't eat, but they just attract the dissolved DDT, and here's another example, another image of food amplification. Now this image is from an article that I encountered using Google Images, and here at the top is the title and where this article is published. And this really makes the same point. So at the very bottom of this image you have what they call primitive producers. Primitive plants and animals that are the first step in concentrating DDT dissolved in water. And then there's above them there's what they call the primary consumers, which are these types of animals that consume the primary producers. And then there are the secondary consumers, which are small fish, eel, minnow, and all that. They eat the blowfish, clams, mud snails, and all the bay shrimp. And then, so these are really the large fish, and below them are the small fish. And now we have a variety of birds that consume these large fish. And as you look at the common tern, the cormorant, the ring-billed gull are fish at the shorelines on oceans. And osprey is a land raptor. Green heron, I think they exist in southern Florida. So here you have the birds that concentrate DDT and are subject to death because of it. Now here's a new term that I encountered using Google Images. This is called a bioaccumulation pyramid. It's sort of is analogous to the food pyramid that you've seen on food packages. So what this pyramid says is, well, there are tiers. Tier 1 are the zooplankton. They call it planktonic feeders, algae, photosynthetic organisms, corals. That's tier 1. And tier 2 are what they call grazers. These are small fish and small animals, although turtles are certainly potentially large. And then tier 3 are large fish, humans, barracuda, predatory fish. So squids, octopus, and even humans. So this is the pyramid from the very elementary organisms through intermediate animals and finally to the highest level animals. Here's an image from Google Images that shows the amount of DDT and another pollutant, polychlorinated biphenyl, PCB, on different seabirds. And as you can see, some seabirds are vulnerable to having a lot of DDT. Look at the bottom, the glaucous gull, whatever it is. And so here's a whole series of seabirds, and here is how much DDT and PCB is in them. I like this image. This is my favorite image for demonstrating biomagnification. And in a sense, this is similar to an image or two I've shown. Let us start with a value of 1 for the concentration of DDT in water. Well, producers, zooplankton, algae, producers, I'm not quite sure what they are, they concentrate the DDT by a factor of 1,000. And the zooplankton consume the producers, whatever they are, and they further concentrate the DDT, so you have a ratio in parts per million of 10,000 here to 1 in the water. Small fish eat the zooplankton, large fish eat the small fish, and fish-eating birds eat the large fish, both in lakes and in oceans near shorelines. So when you go from water to fish-eating birds, the magnification in the DDT concentration is a huge 10 million, which is awesome. By the way, note that DDT is not reacting at any of these levels. It is highly unreactive. It stays in ecosystems for a long time, and all it does, at least here, is move from one location to another. And in this image, you can observe that there are 1, 2, 3, 4, 5, 6 different locations. And this is an example of what I mean, that for a single selected molecule like DDT, in nature it can be present in multiple locations. And that, in my opinion, is chemical engineering, which is part of enrichment chemistry. So let us apply my enrichment chemistry concepts to this DDT ecosystem. First question, what is the identity? And that's simple, the molecule DDT. Next question, what are the locations? Well, you've seen them. Water, zooplankton, small fish, large fish, fish-eating birds. And what is the DDT doing? Well, it is moving from one location to another, and it certainly does not undergo reactions. It's inert. And then a much more difficult question, which requires analytical chemistry measurement, is the amounts in these different locations. And as you've seen on the preceding image, the amounts vary enormously from 0 point something parts per million in water to 25 parts per million in birds. Well, we got a lot of DDT everywhere throughout the world, certainly in the United States, South America, Southeast Asia, and Africa. How did it get there? Well, it was manufactured in large quantities starting in the 1940s. And let me show you how it became present in ecosystems. Now, I enjoy this series of slides because some of them are really amazing. So here's one obvious method, spraying of agricultural fields. Here's another one. Here we have a fogger, a truck that goes up and down the streets of residential neighborhoods and provides a fog that settles on lawns and tree leaves and is supposed to serve as an insecticide. Here in the lower left corner you see workers with nozzles that are spraying DDT in a field. But they're better images. So here at the top left is a fogger And here you have two people, I think they're two women, who are enjoying the fog spray. Hey, it's cool. And after having the spray, I will have no insects on me. And even more remarkable and hilarious is this image in the lower right-hand corner. Here we have a public swimming pool, and here we have a DDT fog generator, and it is spraying the swimmers. And why did they do that? Simple. They thought that polio was caused by insect bites. So how do you solve that problem? Well, you apply DDT and kill the insects. And here you have all the swimmers saying, hey, this is cool. I will be bite-free and I will not get polio. Well, inside the home, you'll find DDT, and here's a product called Black Flag Aerosol Insect Sprayer. Pretty dangerous product because you spray within the house and you are very likely to inhale the spray droplets, which are dangerous. So how dangerous is DDT? Well, here's a summary that I got from Google Images. Here at the upper right is the structure of DDT, and here are all the issues. An organochlorine insecticide, very nonpolar, which means it doesn't dissolve in water. It was banned in most developed countries in the 1970s and 80s. That was decades after it was first used in the 1940s. So it took us decades to figure out that it was dangerous and why. And in humans, it's now known to cause birth defects, damage to nervous systems, and cancers. And in the poorer countries, it's still used, which is a worldwide problem. And here is a can of DDT powder. You spread the powder over blankets and on floors and walls inside residences. Here's a quote I found using Google Images, and I think it's an excellent quote. Popular by E.B. White, a famous scientist. And I like the sense, our approach to nature is to beat it into submission, which is what we've been doing until now, the 21st century, when we are more thoughtful about what we are doing. Can't say we are successful at eliminating, beating into submission of nature, but it's a lot better now. Here's an example, the icon of the United States, the American bald eagle. It's a beautiful, large bird. The problem is that the bald eagle eggs, because of the accumulation of DDT in eagle fatty tissues, the eggs are, the shells are very thin, the embryos are mutated and dead. Here's another example of a nest. You have hatched eggs, and look at the dead hatchlings. Well, it took until 1960, after 15 to 20 years of DDT spraying, for a scientist to spread the message that we are killing birds, and if we kill the birds, they don't sing in spring, there are no hatchlings, and we have a silent spring. Well, the author of this breathtaking book is Rachel Carson, and I think she published it in 1960. So here is a bio of Rachel Carson. She was a biologist, ecologist, and excellent writer, and really way ahead of her time. In fact, Rachel Carson started the whole environmental science movement. One person who made a difference. And I have a couple of quotes, and I don't think I will repeat the quote. I'll just leave this image here for a few moments so you can read it. Here's a second quote. The point is, we are not spraying robins directly, but they accumulate DDT indirectly by eating earthworms, which have DDT in their fatty tissues. And here is a third quote. Well, recently we had the 50th anniversary of Rachel Carson's classic book, Silent Spring. And this scientist is honored by being on a postage stamp, which I show here in the bottom image. And I obtained this image from the website with the URL given here at the bottom. The font size of this text is too small, so it probably is difficult for you to read it, but this is a very good summary of the impact of Silent Spring. So I will stop for some seconds and give you an opportunity to read it. Rachel Carson makes the point that citizens should become better informed in aspects of sciences so they can make informed judgments that impact political decisions. And this is really a good argument for why I believe that enrichment chemistry is an important approach to teaching chemistry. We apply enrichment chemistry concepts to molecules in our environment, and a knowledge of such concepts will make us better informed citizens. I would like to mention one book which I really like among the multitude of books, and it's called Chemistry: An Environmental Perspective. I consider this hardcover book to be a unique general general chemistry book, and I recommend it highly to you. It is available at Amazon.com. Finally, I thank you for listening to this YouTube presentation, which is my first in my enrichment chemistry series on YouTube. Good day.